ఇంకా ఏసీ అని చెప్తా రిమోట్ తీసుకో.
Okay, good evening to all. So I will start the class now. So today we will discuss the measuring instruments that are so we will discuss three measuring instruments: permanent magnet moving coil, moving iron, and Wheatstone bridge. So I will start with permanent magnet moving coil. So let me see, do I have any image? So this is permanent magnet moving coil. So permanent magnet moving coil, it is a meter. Okay, so you know meters. Meters are used to measure the quantities, such as in our laboratory. In our laboratories, we use meters to measure the voltage or current. So permanent magnet moving coil meters, they are used to measure the voltage or current. So we can even call them permanent magnet moving coils. They are also called as galvanometers. Okay, they are also known as galvanometers, or they are also known as the Arsenal meters. Okay, so PMMC. Okay, permanent magnet moving coils. They work on the principle of D'Arsenal principle. Okay, so these are the measuring instruments. PMMC meters are the measuring instruments which measure the current or voltage. Okay, through a coil. Okay, so they measure the current or voltage through a coil. Okay, the coil will have angular deflection here. So if you see here in this image which I am showing you here, if you carefully observe on the right side image, if you carefully observe here in this image, you can see a coil here. So this coil will have angular displacement. Okay, so depending on the angular displacement of this coil, is my voice audible? Is there any issue with my voice matching with the screen? If is my what to say, screen freezing? If there is any issue, just mention in the chat box. Okay, so if you mention in the chat box, I will try to rectify it. Okay, I'll try to rectify it. So in these meters, they are the measuring instruments, so which measure the current or the voltage. So in these meters, what will happen is when current flows through a coil, there will be an angular displacement in the coil. So the coil will deflect. Okay, and when the coil deflects, so actually this coil is placed in between two magnets. You can see here there is a north pole and south pole, N and S. I will expand the screen. So you can see here. So this is where is the cursor? This is north pole and this is south pole. So in between the poles, a coil is placed. Depending on the angular deflection of this coil, which is placed within these poles, if two poles are there, that means that there is a magnetic field between the poles. So when the coil is rotated in the magnetic field, okay, the pointer which is attached to this spindle to which this coil has been attached, that will move. When the pointer moves, the required current or voltage is displayed. Okay, so since here we will use permanent magnets here, so this north pole and south pole, they are the permanent magnets. We know the magnets. Okay, so we know the difference between magnet and electromagnet. Okay, so we won't use any electromagnet here. We are going to use the permanent magnets. So since this coil is placed inside the permanent magnets, that's why this instrument is named as permanent magnet moving coil instrument. So the name, what is the name of this instrument? Permanent magnet moving coil instrument. Okay, So why this name is given? Why? Because there will be a permanent magnet inside this instrument, and the coil inside the instrument will be moving. Okay, there will be permanent magnet inside the instrument, and the coil inside the permanent magnet will be moving. That's why this instrument is named as permanent magnet moving coil instrument. So which is used to measure the voltage or current. So this permanent magnet, which is here within this instrument, it creates the stationary magnetic field. Stationary means if anything is not moving, then that is stationary. So here the magnetic field that is induced between this north pole and south pole, that magnetic field will be stationary. Okay, so this permanent magnet, north pole and south pole magnets, they will create a magnetic field. These are the magnetic flux lines. You can see the magnetic field here. In this image, you can see the magnetic field. You can see straight lines traveling from north to south. So these are the magnetic flux lines which are traveling from north to south. So they are the stationary magnetic field. Okay. So when this coil, you can see. So you can see the coil here. So when this coil, you can see this is our coil. This dark black color. I'm sorry, my cursor won't listen to me. So you can see a coil here. This is our coil. So which has some n number of turns. Okay. So I'll better, instead of pen, I will take the laser pointer. You can see here there are some n number of turns, dark black color coil you can see here. Okay, so this is the coil. So when this coil is rotated in the magnetic field, okay, what will happen is torque is induced. Okay, torque is induced. The coil will experience the torque. So there will be an angular displacement. Okay, here. So so I hope you people know what is meant by torque. Torque is the measure of force that can cause an object to rotate around an axis. So what will happen to the coil here? It will experience a force that will cause this coil to rotate about an axis. Now first of all, before going in detail into this concept, let us see what are all the parts does this permanent magnet moving coil have. Okay, so let's go to the yeah. So if you see here in this image, you can see here one. So this one, you just see this one. This one is nothing but external shield. Okay, this you can see a cylindrical structure here. This cylindrical structure, this is it. This cylindrical structure, what you can see here, it is the external shield. I'm sorry. Okay, it is the external shield. You can see here, this is one is external shield in this permanent magnet moving coil. Next, 2 is permanent magnet. Let us see what is the 2. So what is 2? This is it. This is the permanent magnet. Okay, 2 is the permanent magnet. Next, you can see 3. Here 3. So 3 is the moving coil. Okay. So here 3 is the moving coil. Next, here you can see 4. 4 is the spring. So this is some photo which I got from somewhere. Okay, so I don't know whether it is clearly visible. If you carefully observe here, there is a spring-like structure below 4. So you just carefully observe here. See, you just carefully observe here. If you observe, you can see spring-like structure. So 4 is the spring. It is known as control spring. And if you see 5 is the pointer. So in our laboratories, you can see pointer moving. When you apply some voltage or current in the meters, you might have seen the pointer moving. So okay, this 5 is the pointer, and the 6 is the arrangement of zero balance of the pointer. So let us discuss in detail about this. So if we simply have explained the parts, but looking at this image, we can't clearly understand how these parts, the actual shape of these parts is. Okay, so for that, see in this image, so you can see a pointer. Okay, these are PMMC, permanent magnet moving coil instrument. So this is the pointer. Okay, so this black color line, this is the pointer. So here there will be a mirror. Okay, there is a mirror in the PMMC to see what? To see the readings. So there is a scale here. You can see the scale. So to take the readings of voltmeter or ammeter. Okay, so PMMC is used to measure only DC current or voltage. So this is the mirror through which we will take the readings. I hope you can recall what you do in our laboratories. So next, so just now I have told you in the previous image there was a moving coil or control sorry, not moving coil. Yeah, so moving coil was there, so it was not visible there clearly. If you observe here, this copper structure here, if you carefully observe in this image, so here this portion, so some yellow or brownish color portion, this is the coil. Okay, so you just observe carefully this image. This is the coil inside portion. This from this S, besides to S, you can see here some copper color structure is there, and besides to N also you can see behind this spring. Behind this spring, if you carefully observe, you can see the copper coil. Okay, so only the top view of the copper coil is visible. So that is our moving coil. Okay. Next, you can see the spring clearly. This is our spring, which is clearly visible, isn't it? This is the spring of this permanent magnet moving coil instrument. So this is the spring, and this is the dial. Okay, from which we will take the readings. Okay, this is the scale, or we can say scale or dial. So from this we can take the readings. Okay, and this is South Pole and this is North Pole. So what is it? It is our permanent magnet. South Pole and North Pole, they are our permanent magnets. Okay. Okay then. So let us discuss the operation, construction and working of this instrument. So this permanent magnet moving coil instrument is most accurate type of DC measuring instrument. So okay, it gives us more accurate values. So here what I have already told you that the parts of the permanent magnet, you can see North Pole, South Pole. So permanent magnets are connected here, and if you observe here, these are the black color lines, they are the coils. So you can see moving coil, and this is the spring. You can see a spring at the bottom, and you can see an upper spring also, spring at the upper portion. Okay, and this is our scale, and this is our pointer. Okay, and this moving coil is wounded. It is wounded across an iron core. Okay, it is wounded across an iron core. So this moving coil, it can be of rectangular shape. If you observe here in this image, this coil, if you observe, it is in rectangular shape, isn't it? The shape can be rectangular or circular. Okay, the shape of the spring, it can be either rectangular or circular, but here in this image it is rectangular in shape. Okay, and this coil will have, it is made up of fine wire, thin wire, and it will have some n number of turns. If you carefully observe here, it is having some 1, 2, 3 and 4 turns. 4 turns are there, just for example. There are 4 turns here, but it can have some n number of turns. Okay, this coil can have n number of turns. It is made up of thin wire. Okay, this coil is suspended such that it is free to turn about its vertical axis. Okay, vertically it will be able to freely rotate. Okay, that's how it is suspended in between these two magnets, in between the north pole and south pole. So my cursor, okay, in between north pole and south pole, it is suspended in such a way that it can rotate vertically. Okay, so the magnetic field that is induced between the north pole and south pole is which is the magnetic field that is traveling from north pole to south pole is uniform, and it is horizontal, and it is radial. Okay, the magnetic field between the north pole and south pole. Okay, so and the magnet that is used here, that magnet is in the shape of horseshoe. If you observe here, this whole U-shaped structure, it is the shape of the horseshoe. So the permanent magnet that is used in the PMMC instrument, permanent magnet moving coil instrument, that magnet is in the shape of horseshoe. Okay. Now here I have told you that this moving coil is wounded across the iron core. So this is our iron core, and around it moving coil is wounded. Okay, so this iron core, depending on the shape of the coil, the iron core shape will change. Now if the iron core is spherical, okay, so if the iron core is spherical, then coil will be circular. If the iron core is cylindrical, the coil will be rectangular. So if you observe here, the iron core is cylindrical, isn't it? The iron core, how is it? This yellow color portion, it is cylindrical. Iron core is cylindrical in shape. That's why moving coil, if you observe in this image, it is rectangular in shape. Okay, so moving coil shape will depend on the iron core shape. So if iron core is cylindrical, moving coil will be rectangular. If iron core is spherical, then moving coil will be circular in shape. Okay, so here what will happen when the coil rotates? What will happen is torque will be induced. Okay, so the torque that is induced here, that is known as deflecting torque. So the deflecting torque that is induced here is mainly due to the iron core. Okay, so because of this iron core, the sensitivity of the instrument will increase. Okay, so because of the deflecting torque, so what do we want to deflect here? We want to deflect, one second, where is my, yeah, we want to deflect the pointer from 0 position. We know this is our 0 position and this is our scale, and maybe its range can be around whatever, it depends, it can be a 5 amperes ammeter. If it is an ammeter, its range can be from 0 to 5 amperes. So this pointer, from it will be initially at 0 position, isn't it? This pointer will be initially at 0 position. It has to be deflected depending on whatever current it is measuring, if it is an ammeter. So the deflecting torque means it is the torque which moves the pointer across the scale, okay, in an analog measuring device. Analog means there will be proper scaling provided to take the readings. Digital means value will be directly displayed on the screen. Okay, so that is our deflecting torque. Okay, so the deflecting torque, when the coil is rotating, automatically what will happen? The pointer will also move from its initial position, from 0 position. So the torque that is induced here, the deflecting torque that is induced here, it will increase due to this iron core. Okay, and the instrument will be more sensitive because of the presence of this iron core. Okay. Now once the torque, deflecting torque is induced, pointer has started to move from zero position. Okay, from zero position, from suppose this is zero, from here, sorry, my cursor is, this is my zero position. From here, the pointer had started to move and it has to stop at this location. Okay, at this reading. Suppose my current is, some 1 ampere or 2 amperes, whatever. Okay, if suppose my current is around maybe some 2 amperes. Okay, so as soon as 2 amperes, as soon as 2 amperes appears, the pointer has to stop. Okay, it should not move further. Okay, so for that, another torque should be induced within this instrument. The torque is known as damping torque. Okay, so damping torque will oppose the deflecting torque. The purpose of the damping torque is to oppose the deflecting torque. Okay, so it is similar to what we do. We walk on the floor. When we walk on the floor, there will be friction with respect to the surface, isn't it? That's why we won't slip and fall down when we are walking. So if there is no friction, we will slip and we will fall down while walking. Similarly, if there is a deflection torque, if the pointer is moving from its zero position, to the required current or voltage value, it has to stop accurately at the value that we are measuring. So there should be another opposing torque to the deflecting torque. Okay, that is known as damping torque. So this deflecting torque is provided by the spring. Okay, the springs are connected here, you can see here. So the controlling torque or deflecting torque is provided by the spring. So the controlling torque or the, sorry, damping torque, not deflecting torque. Damping torque is nothing but our controlling torque. So it is the torque that controls the pointer on this scale to a specific value that is proportional to the quantity that is being measured. That is the definition of your controlling torque. Okay, so while I'm explaining, if people draw this diagram, so I have been showing this diagram. So people draw it in some notes. If you don't have your, you just draw in some notes so that it will be useful to you. Okay. So till now, how many torques that we discuss? One torque is deflecting torque, another torque is damping torque or controlling torque. The controlling torque is provided by the springs that are connected in this instrument. Okay. So when this the coil which is wounded around the iron core, that coil, it is actually not directly placed on the iron core. There will be a rectangular sheet on the iron core on which this coil is wounded. Okay, there will be a rectangular sheet on the iron core. So I will show you another image which I have shown earlier. So I will show it to you. So if you see here, some green color portion that you can see here, so which is rectangular in shape, on which this is my coil. This is coil, moving coil. Okay. So this is coil. This green color, what you can see, is the former. That is known as FORMER. That is former. So I'm unable to write. Okay, that is former. What is this? This silver color, what you can see here is the iron core. Okay, so this is iron core. So on the iron core, this cylindrical structure you can see in this image, that is the iron core. And on the iron core, there is this green color portion. What you can see is the former. It is made up of aluminium. Okay, former is made up of aluminium. So it is a rectangular aluminium sheet on which this coil is placed. Coil is also rectangular in shape. So because core is cylindrical in shape, moving coil is rectangular in shape. Okay. So this pointer, what you can see here, the pointer is carried by this spindle. You can see there is a spindle here to which this pointer is attached. Okay, and this pointer move on this scale. Okay, and the weight of the pointer will be very light. Okay, so that it can easily deflect, and with the help of the mirror that is placed above, we can easily take the readings without any parallax error. Okay, so we should take the reading without any parallax error. We should know means we must exactly stand in front of the mirror and carefully take the readings without any error. Okay, so here the scale marking. So you can see here, where is my pointer? Yeah, you can see scale marking here 0, 1, 2, 3, 4, 5, 6 up to 10, whatever scaling that is provided. Usually the scaling is a linearly spaced scaling on this scale. On this scale, what you can see here, it is the linearly spaced scale. So the scaling is placed linearly. Okay, so depending on the deflecting torque that is induced. Okay, here deflecting torque will be induced, and as well as the, of course, controlling torque will also be induced. The scale marking of this PMMC instrument, which measures only DC current or voltage, are usually linearly spaced as the deflecting torque, and the pointer will move according to the deflecting torque. Depending on the deflecting torque, how much torque that is induced, based on that the pointer position will move. So the depending on the deflecting torque, as the pointer is moving, the deflecting torque will be proportional to the current passing through the coil. Okay, so of course we will give some current. So whatever current passes through this coil, this is our coil, isn't it? This is our coil. So how much current is passing through the coil, depending on that, the torque, deflecting torque that is induced will cause the pointer to move. So if I want to apply 4 amperes, just for example, according to this image, so if I am applying 4 amperes, and if I want this pointer to move from 0 to 4, okay, so whatever deflecting torque that is induced in this device, that deflecting torque will cause the pointer to move from 0 to 4. So the whatever deflecting torque that is induced, it will be always proportional to how much current that is flowing through the coil. Okay, so if you see the working, so let me show one more image. So I'll show this image so that if you people were drawing this, you draw it. Okay, so the action of this permanent magnet moving coil instrument is based on motoring principle. Motoring principle means what? So when a current carrying conductor is placed in the magnetic field, what will happen? It will experience the force. That's what motoring principle is. What is the function of a motor? Function of a motor is to convert electrical energy into mechanical energy. That's what this motor does. So what does it do? It converts electrical energy into mechanical energy. That's what here happens. So see here there is a moving coil. Cursor. This is the moving coil. This is the moving coil. So when current passes through the coil, depending on the current, deflection torque is induced. So when current passes through the coil and this coil is placed in the magnetic field, it will experience the force. Okay, so it will experience the force. So that image is there somewhere. Motoring action, somewhere it is there. So this is it. In this image, if you see, this is North Pole. This is North Pole. This is South Pole. So if you see carefully, this is South Pole. If you see carefully, it is similar to the armature of your DC motor, isn't it? So in the this iron core looks like the armature. This is the coil, okay, rectangular shaped coil. And these are the magnetic flux lines. Okay, this is North Pole. This is South Pole. This circle is the iron core, and this rectangular shape is the moving coil. Okay, so we are looking at the top view of this image. So if you see carefully, these lines, they are the magnetic flux lines. So when current is passing through this coil, when current carrying conductor is placed in the magnetic field, what will happen? It will experience the force, and what will happen when it is experiencing the force, then motoring action takes place. So permanent magnet moving coil instrument, it works on the principle of motor. So its operation is based on the motoring principle. Okay. So as the coil is moving and permanent magnets, they are not moving here. Okay. And since it is operating on the motoring principle, you can even call this sort of operation on this principle as D'Arsonval principle. As I've already told you, it is also known as, somewhere it is written, I have written somewhere. Okay, the principle at which with which it operates. So simply motor principle. So you can say D'Arsonval principle. This sort of operation is known as D'Arsonval principle on which this operates. Okay. So the torque that is induced in the coil will be always directly proportional to what? How much current is flowing through the coil. Depending on the current flowing in the coil, the torque will be induced. Okay, so this is how this device operates. Okay, so this is our core. This is the front view. This is the core. Around it there will be a former, that is aluminum sheet, above which coil is placed. These are the magnets, North Pole and South Pole. So when current passes through the coil, what will happen? Due to motoring action, the coil will rotate and torque is induced. When torque is induced, what will happen? The pointer, if you see in this image, the pointer which is attached to the coil, it will move. The pointer will move, and up to what distance it has to move, it will depend on how much current is flowing through the coil. Up to what distance it will move, it will depend on how much current is flowing through the coil. And in order to control the movement of the pointer, there are springs connected. So higher springs, okay, higher springs you can say, it will control the movement of the coil. Okay, so if you have understood, this is one more image, okay, of the permanent magnet moving coil instrument. So this image I have already shown you. Okay, this is one more image. So the shape of the magnet will be like an horseshoe. So if you know the shape of the horseshoe, you can easily see just U-shaped structure. Horseshoe will be somewhat U-shaped in structure. So this is one more image. Okay, so if you are able to follow, were you able to understand or not, you just mention in the chat box, or shall I proceed? Okay, so it is usually used in AC galvanometers, okay, flux meters. These applications of this, okay, permanent magnet moving coil. They are used as ammeters as well as voltmeters, which I have already told you. Okay. They are based on they are utilized in the construction of AC galvanometer, flux meters and ballister galvanometers. Okay, that is it about the permanent magnet moving coil instrument. This is one more image. Okay, so if you have understood, if you want me to repeat, you just type repeat. If you have understood, type understood. Okay, or shall I move to the next topic? Moving iron instrument. So if you want, I can briefly once again explain the operation of this permanent magnet moving coil. So yeah, from this image, permanent magnet moving coil will have a horse-shaped magnet. Okay, it will have a horse-shaped magnet. I will take laser. This cursor is not listening to me. Horse-shaped magnet. Okay, and it will have since we are using permanent magnets here, therefore the therefore this permanent magnet moving coil instrument is named as permanent magnet moving coil. Coil moves, permanent magnets are used, so that's why it is named as permanent magnet moving coil. So there is a north pole and south pole, in which in between them there is an iron core. On the iron core, former will be there, aluminum rectangular sheet will be there, which is not shown in this image. Okay, on the rectangular sheet of aluminum, spring is coil is placed. Okay, and there you can see an handle here on which this coil is suspended, and this you, if you observe carefully, there is a some triangular shaped structure below and above. They are the counterweights. Okay, they are the counterweights. So whenever current flows through the coil will rotate. Deflecting torque is induced in the magnetic field. So when the deflecting torque is induced, the coil rotates. Hence, this handle which is to which it has been attached, it will rotate, and hence the pointer will rotate from 0. Okay, and the deflecting torque will be proportional to the current that has been applied. So when the pointer rotates, the pointer should stop at some point. Okay, so the pointer should stop at some point. So in order to stop the pointer, in order to control the deflection of the pointer, the what is it, damping torque or controlling torque is induced by the springs that has been attached here to this handle. Okay, the springs that has been attached to this handle. So controlling torque will always oppose the deflecting torque. Okay, so as soon as sufficient means as soon as the required current reading has been obtained, immediately the pointer will stop due to the damping torque. This is the operation of your permanent magnet moving coil, and it always gives the accurate reading. That's why it is preferred. Okay, so let me go to the next topic, that is moving iron instrument. Moving iron instrument. Okay, so moving iron instruments, they are used for measuring the flow of current or voltage. Again, similar to your permanent magnet moving coil instrument, moving iron instruments, they are also used to measure the current or voltage. Okay, and they are also known as MI instruments. So you can see I am showing an image of an ammeter here. So they can measure both AC current or voltage or DC current or voltage, whereas permanent magnet moving coil instrument can measure only DC. Okay, they can measure only DC parameters, DC current and DC voltage. But moving iron instrument, they can measure both AC current and AC voltage. Okay, so and if you observe carefully, the scale, if you observe in this ammeter which I am showing you here, if you just observe the scale. Okay, you just observe the scale here. There are no much lines between 0 to 5. You just observe here 0 to 5. So you just observe the scaling from 0 to 5 of this ammeter. If you observe here, there is no proper scaling. Okay, you just observe the scaling from 5 to 10, 10 to 15, and 15 to 20. So the for moving iron instruments, the Okay, so the charging of my laptop was it was over. It was 0. That's why I was disconnected. It's okay. Now we can continue. So I can continue the class. So now just observe the scaling of this uh, ammeter, which I'm showing you here. I will just expand the screen. You just observe the scale of this moving iron instrument, which I'm showing you here. So just observe the scale from 0 to 5, 5 to 10, 10 to 15, 10 to 15, and 15 to 12. Just observe the scale. If you observe the scale is non-linear, isn't it? Non-uniform actually. So okay, the scaling of moving iron instruments will be non-uniform. Okay, so this moving iron instruments, this is the internal diagram of moving iron instrument. So this moving iron instruments will have a moving iron. Okay, so in your previous case in PMMC there was a moving coil. In this moving iron instrument there will be a moving iron piece that moves in response to the magnetic field generated by the current flowing through the coil. Okay, so if you see here, these are the coils. These are the coils, coil winding or coils. Okay, these are the coils. Here coils are there, here also coils are there. Depending on how much current flows through these coils, this moving iron, this is our moving iron, it will move. Okay, so the moving iron will move depending on the current flowing in the coil. Okay, this is our moving iron. So the movement of the moving iron will depend on how much current is flowing through the coil. Okay. Okay. So what happens here is when current is flowing through the coil, here magnetic field will be induced. Okay. So when current flows through the coil, magnetic field will be induced. So when okay, so magnetic field will be induced, and the magnetic field strength will depend on the current flow in the coil, and the movement of the moving iron will depend on the strength of the magnetic field, or indirectly on the strength of the current flowing through the coil. Okay, so these are our electromagnets actually. These are our electromagnets. So you know what is meant by an electromagnet. When a coil is wounded around a ferromagnetic material, it becomes an electromagnet. So when current flows to the coil, the ferromagnetic materials gets magnetized. Okay. So MI instruments, moving iron instruments use the electromagnets interaction between the current carrying conductors and the moving iron element to translate electrical values to the uh, into the mechanical movement, thereby providing a visual representation of the various electrical parameters such as current and voltage. I hope you didn't understand what I just spoke. So what will happen here is, where is I'm unable, this is my cursor. So what will happen here is, so these are the current carrying coils. You can see small circular portions here. They are the current carrying coils. So when current flows through this coil, this ferromagnetic material, this rectangular or this U-shaped structure, they are the ferromagnetic material. They gets magnetized. So magnetic field is induced. So when magnetic field is induced, and when an iron piece is placed inside the magnetic field, this iron piece just moves. Okay, so when the iron piece moves, automatically the pointer which is connected to it, it just deflects from its position. Okay, so what is happening here? Because of the electrical energy, mechanical movement is taking place. Okay, so we are able to take the readings of the meter. Okay. Okay, so the movement of the moving iron, movement of the moving iron is based on how much magnetic field is induced in between these electromagnets. So here magnetic field will be induced. So we already know that iron piece can be easily magnetized. So as soon as iron piece comes in contact with the magnetic field, what will happen? It is easily attracted by the magnetic field. Okay. So if you bring an iron piece nearby to a magnet, what will happen? It just gets attracted. Okay, it goes and attached to the magnet. Okay, that's what happens here. So as soon as current starts to flow, okay, I will take the laser. So as soon as current starts to flow through this coil, this these electromagnets get magnetized and magnetic field is induced. As soon as magnetic field is induced, what will happen? That moving iron will start to move. Okay, it gets attracted towards the magnetic field, it starts to move. When the moving iron starts to move, automatically the pointer will also starts to move. So how much movement will be there in the moving iron will depend on the magnetic field strength. See, if there is a magnet and there is an iron piece, and if magnet is very far away from the iron piece, then the force of attraction will be low. As you bring this moving that iron piece nearer to the magnetic field magnet slowly, what will happen? The force of attraction will gradually increase. Okay, similarly, depending on the magnetic flux lines, if suppose more flux lines are induced here. Okay, if suppose more flux lines, these are the magnetic flux lines traveling from one electromagnet to another magnet. If more flux lines are there, more movement will be there in the moving iron, and hence more deflection will be there in the pointer. Okay, more deflection will be there in the pointer. If the magnetic field strength is low, okay, if the magnetic field strength is very low, very few, I'm drawing only few lines. If the magnetic field strength is low, less movement will be there in the moving iron, hence the pointer will also deflect to means the deflection in the pointer will also be low. Okay, and there is a counterweight balance that is provided here in order to control the movement of the pointer. Okay, so this is our this is some U-shaped structure to balance the weight that has been provided, and scaling will be provided as shown in the previous diagram. This is how non-uniform scale is provided for such type of meters. Okay, so when iron is moving, this movement is transferred to the pointer across the calibrated scale through a linkage mechanism. Okay, so it is linked, the iron movement is linked to this pointer. So you can see how it is linked here. Okay. Okay, and one more thing. So if the pointer is moving, its movement has to be controlled. So its movement will be controlled. Okay, its movement will be controlled by providing some damping action. So this damping action will be provided by the control weight. Okay, the damping action will be provided by the control weight. So here scale of the pointer is not shown. I have another image. In this image you can see this is the scaling of the pointer. Okay, so this is the mechanism that is provided for this pointer as well as moving iron to move. Okay, this is the mechanism they have connected. You can see an air damping chamber. So there is an air damping chamber in which the piston is connected here. This is our piston. So as the moving iron moves, this piston and air damping within the air damping chamber, this also it is moving, and pointer also moves. So all are interconnected. This is how this device has been manufactured or designed. Okay, so this is our control weight provided to control the movement of the pointer. Okay, so as much current as means in the coil, this is our coil, these are our these small round structures are the coils. Okay, so as the current in the coils increases, magnetic field strength increases. If the magnetic field strength is increasing, then the force of attraction between the iron piece and the coils will also, this magnetic field will also increase, and hence the deflection deflection torque, we can say deflecting torque will increase. So, and the damping torque is provided with the counterweight. Okay, and this movement is controlled by this piston and air chamber. So you people can draw this diagram quickly. So actually this is balance weight. It's this here one arrow mark is missing. This is weight 2, weight 1, weight 2, W2, W2, W1, W2 and W3. These are the counterweights which try to control the movement of the pointer. Okay. So in order to get the accurate reading. And how to get the accurate reading. So you people can draw this. Just draw this diagram as quickly as possible. So here what is happening? Meanwhile, you people are drawing. I will just discuss few more points regarding this. So when current passes through the coil, okay. So when current is passing through the coil, so when current passes through these coils, you can see C. C represents coils. So when current passes through these coils, what will happen? Magnetic field is induced. Okay, when magnetic field is induced, this field will create a force of attraction towards this iron piece. Okay, so the magnitude of force of attraction between this magnetic field and iron piece, because of this force of attraction, there will be movement in the iron, and this iron movement of the iron will be directly proportional to this movement of the iron will be directly proportional to always square of the current. Moment of the iron will always be proportional to square of the current flowing through the coil. Okay, so I amperes of current flowing through these coils. Okay, I amperes of current is flowing through these coils. So the moment of the iron piece will be always proportional to the square of the current flowing through these coils. Okay, and the force or the torque that is induced here, force depends on the magnetic field strength itself, and the magnetic field strength will depend on what? The current flowing through the coil. Okay, so this moment is mechanically linked to the pointer here. It is mechanically linked to the pointer which moves over this non-uniform scale, so to indicate whether the voltage or current. Okay, so since here the force or the torque that is used, that is moment of the iron, is relatively proportional to the square of the current. So this type of instrument, they can be used to measure both AC voltage or current or DC voltage or current. So this is the operation of moving iron instruments. So one more instrument is left over. So that is Wheatstone bridge. If you complete, just mention in the chat box that you have completed. If you have completed drawing it, you just draw this diagram. So here one more arrow mark is missing. The counterbalance, I'm sorry. So here these three, W1, sorry, this pen, W1, W2, W3. These are the counterweights. They are the counterweights to control the movement of the pointer. These three are the counterweights. Okay. Here you can see control weights it is mentioned. You try to draw as quickly as possible. And we will go for the one more instrument. Okay, I will move forward. So if you have not yet completed, after this class, you go through this video and you just draw the diagram. So our next instrument is Wheatstone bridge. So most of you can recall this Wheatstone bridge. You might have done the experiment in the laboratory on this Wheatstone bridge. So that's why I have put this image on the screen. So this Wheatstone bridge, it is also known as resistance bridge. Okay, so the purpose of Wheatstone bridge is what? What is the purpose of Wheatstone bridge? Can anyone mention in the chat box? Purpose of Wheatstone bridge. What is the purpose of Wheatstone bridge? What is the purpose of Wheatstone bridge? Can anyone just mention in the chat box? Those who know, just mention in the chat box. I will continue. So Wheatstone bridge is used to determine the unknown resistance. So it is also known as resistance bridge. So it calculates the unknown resistance by balancing two legs of a bridge circuit. Okay, by balancing two legs of a bridge circuit. So you can see here in this image, this is our bridge circuit. So this is our bridge circuit. See here what happens, two legs of the bridge circuits are balanced to determine the unknown resistance. Okay. Among this four, you can say this is a bridge circuit. Among these four resistors, you can see P, Q, R and S. Among these four resistors, one is the unknown resistance. Okay. So here in this image, this R, whatever it is shown here, R is our unknown resistance. Okay. So this Wheatstone bridge was invented by Samuel Hunter. Okay. In 1833. Okay. And it became popular in the year of 1843 by some Charles Wheatstone. Okay. So this Wheatstone bridge will be consisting of two known resistors, one unknown resistor and one variable resistor connected in the bridge. So here if you see, there is a variable mark on S. Okay. So this variable mark on S represent that this is our variable resistance. R is our unknown resistance. P and Q are known resistors. Okay. P and Q are known resistances. And this bridge is very reliable bridge as it gives us accurate measurement. Okay. So this bridge here 1, 2 and 3 and 4 resistors are there. They are known as 4 arms. So this Wheatstone bridge consists of 4 arms. Okay, and these 2 arms are having a known resistance. This arm has a variable resistance. This arm has unknown resistance. Okay, and this bridge will also be having a meter which is known as galvanometer. You can see G symbol here. You can see G here. So that is the galvanometer. So if you want, I can show you another image. This is it. This is our galvanometer. Okay, you can see here. This is our galvanometer. And it also consists of source or battery. So you can see in this image, so external battery it is mentioned here. So external battery. So it consists of an external battery and a galvanometer. Okay, so it can even have internal battery also. Okay, so here in this image, so this is our source E and this is our galvanometer in this bridge. This is our source and this is our galvanometer, source and galvanometer. Okay, so this source E, it is attached to this bridge at point A. It is attached to the bridge at point A and point C, while the galvanometer is connected between point B and point D. Galvanometer is connected between what? Point D, B and D. Okay, so once again I will repeat. The source E is connected between point A and point C. Okay. Source is connected between point A and point C, whereas galvanometer is connected between point B and point D. Galvanometer is connected between point B and point D. So now for the current to flow in the galvanometer, okay, if for the current to flow in this galvanometer, it will depend on potential difference between point B and point D. Potential difference means what? It is the voltage difference between point B and point D. If voltage at B is V1, if voltage at D is V2, okay. So I will just write it. If suppose voltage at B is V1, voltage at D is V2, okay. So if there is difference between V1 and V2, if there is difference in voltage between if V1 is not equal to V2, so then the difference between V1 and V2 will cause current to flow through the galvanometer. If suppose V1 is equal to, if V1 is equal to V2, then if V1 is equal to V2, so current in the galvanometer, Ig, suppose Ig is the current. Okay, current in the galvanometer is how much? Ig. So this Ig will be equal to 0. No current will flow. Okay, if V1 equal to V2, no current will flow through this galvanometer. Okay, no current will flow through this galvanometer if V1 is equal to V2. So there should be a potential difference between B and D for the current to flow through the galvanometer. Okay, so this Wheatstone bridge, you know, it works on the principle of null deflection. Okay, null deflection means zero deflection. Okay, so the ratio of the resistances, okay, if the ratio of the resistances in this bridge circuit are equal, if the ratio of the resistances in this bridge circuit are equal, Okay, if the ratio laser, I'm taking laser. If the ratio of these resistances in this bridge circuit are equal, so then there will not be any deflection in the galvanometer. It will be zero. If the galvanometer is showing deflection zero, that means that there is no potential difference between B and D. Okay, so we can say this bridge is balanced if galvanometer shows no deflection. It is not showing any deflection means its deflection is zero. So if the galvanometer shows zero deflection, then we can say that the bridge is balanced. So this Wheatstone bridge works on this null deflection principle. Okay, that null deflection means what? The ratio of the resistances are equal and no current will flow through this galvanometer. Okay, so under normal operating condition, the bridge is unbalanced. Okay, and current will flow through the galvanometer under normal operating condition. Okay, so the bridge is said to be balanced when no current flows through this galvanometer. So this condition, it can be achieved by adjusting the unknown resistance and variable resistance. If I want this bridge to be balanced, okay, then I should make sure no current flows to the galvanometer. Means the potential difference between B and D should be equal to 0. Means this V1 should be equal to V2. So that can be achieved by simply varying this variable resistance value and unknown resistance value. So if I am able to vary the R value and S value, okay, if I am able to vary the R value and S value, then I can say that the bridge is balanced. Okay, now so I'll take the pen. Now this is my source, isn't it? This is my voltage source. This is my voltage source. Now current will start to flow from this positive terminal till current will flow through this positive term, start to flow, come out of this positive term, it will flow like this. It will flow like this and it will flow like this. When it reaches terminal A, what should happen? Current should divide. At terminal A, current will divide into two parts. So what is the current entering this resistance P? How much current enters resistance P? I1 current. And how much current enters this unknown resistance? I2 current. Okay. So I2 current is flowing. Okay. I2 current flows through R. I1 current flows through P when current enters this junction A. Okay, so when the bridge is balanced and no current flows through the galvanometer is showing zero deflection, then at that condition, okay, the voltage, okay, the voltage in this branch, AB branch, should be equal to the voltage in AD branch. Voltage in AB branch should be equal to voltage in AD branch. That means that what is the voltage in AB branch? Current I1 . Okay, so if this is I, current I1 into P is the voltage in AB branch, it should be equal to current I2 into R. I1 should be equal to I2 into R. Okay, so you people quickly draw this image. Draw this image. Bridge circuit. Draw this bridge circuit. Okay, completed. Okay then. So now when the bridge is balanced, okay, so when galvanometer is showing zero deflection, I1P should be equal to I2R. Okay, so voltage in this branch should be equal to voltage in this branch. So it is there in the next slide. So you can see I1P should be equal to I2R. Consider it as equation 1. Okay, consider it as equation 1. Okay, now since here, as I said, so as I said, no current flows through this G galvanometer. So whatever current entering P, same current will enter Q. Whatever current entering R, same current will flow through S. Okay, same current will flow through S. So current I1, here what should happen? Current should flow through P. At B, current should divide. But current will not divide because here no current flows through the galvanometer. Okay, no current flows through the galvanometer. So we can assume that this galvanometer is not existing. Okay, you just neglect it. So whatever current flows through P, same current will flow through Q. Whatever current flows through R, same current will flow through S. That means that I1 is equal to I1. This I1 is equal to what? I3. Okay, that's what I'm trying to write here. Okay, I1 equal to I3. Similarly, I2. I2 is equal to what? I2 current will be equal to I4. I2 current will be equal to I4. This cursor, this. Okay, so I2 will be equal to I4. Okay, why I1? Where is I1? This is I1. It is equal to what? I3. Why? Because no current flows through galvanometer. So whatever current flowing through P, same current will flow through Q. Okay. So whatever current is flowing through R, same current will flow through S. So I2 equal to I4. This is I4. This is I2. So I2 equal to I4 and I1 is equal to I3. So that's why. So you can write current equations. I1 is equal to what? I3. So what is current equation? Voltage by resistance. What is resistance? P plus Q. And I2 equal to I4. So voltage by resistance R plus S. So voltage source. You can see in the above figure. You can redraw the diagram like this. This is my source E. This is my source E. So I am drawing like this. So this is my resistor. This is my one resistor, another resistor. This is my one resistor. I'm sorry. This is one resistor. This is okay, I'm unable to draw the resistor here, but Okay, this is it. So this is my source. This is how current will enter. This is my P and this is my Q. This is my R and this is my S. So same current will flow through P and Q and R and S. So what about the current? I is equal to V by R. V is what? E. E is parallel to what? P and Q. So E by PQ. Similarly, E is parallel to R and S. So E by RS. Okay. So these are the current equations. These are the current equations. Now substitute this above equations in your equation 1. Substitute these equations in your equation 1. What was your equation 1? Your equation 1 was this. I1P is equal to I2R. Substitute in this equation. Okay, so what I can do is, I will just copy this from here. So you can see I1 P. So P into what is I1? E by P plus Q, right? E by P plus Q. So R into I2. What is I2? E by R plus S. So substitute it here. Okay, substitute it, and you can cancel E. You can see E is there on both sides. So cancel E. So just cancel E. What will happen? You just remove E. E cancel. What is left over? P by P plus Q, R by R plus S. Just to rearrange the terms, just simplify it. Send P plus Q to the right side, R plus S to the left side of this equal. And you will get P into R plus S and R into P plus Q. Just multiply P with RS. So PR plus PS. And on this side, RP plus PQ. This is what, I'm sorry, RQ. You will get this. Just expand it. After that, okay. So here you can see you have got PR on both sides. So PR, you can cancel them. What is left over is PS is equal to Q into R. So what is R? P by Q into S. Okay. R is the unknown resistance. So you can calculate unknown resistance from this bridge circuit, Wheatstone bridge, when the bridge is balanced. So when the bridge is balanced, what is the formula to determine the unknown resistance R value? Okay, so when the bridge is balanced, so this is our unknown resistance. R is equal to P by Q into S. So R, P and Q and S all are resistance values, where P and Q are known resistance, S is the variable resistance, R is the unknown resistance. Okay, this is how on the Wheatstone bridge the unknown resistance is calculated. When it okay, that is the formula to calculate the unknown resistance. Now let us see practically how to do the experiment. So you can see here, so you can connect an external battery. Here you can see in this image, you can connect an external battery, or if internal battery is available, you can, there will be a switch in this image. What I am showing you here, internal battery is not shown. So definitely you have to connect an external battery here. Okay. So this is our galvanometer. So so here you can see RX. RX is here. You have to connect an resistor, unknown, whose value you don't know. So connect the unknown resistor. So in this image, sensitivity is not mentioned. So sensitivity, you can keep the sensitivity low, medium, or high depending on the requirement. So here So I don't have that image. I think I don't have that image which shows the sensitivity, how sensitive this Wheatstone bridge should be there. That is it available? No, it is not there in this image. So you can set the sensitivity, and you can connect the galvanometer externally or internally. So here there is an internal galvanometer. So you can you just if there is a knob here, it is not, you can just click it to internal and external galvanometer knobs will be there. That is not shown in this image. In this I think this is the old model, but mm, this is what the image that I have got, so that's why I'm showing you here. Now after connecting unknown resistor, okay, so where is my cursor? This is it. So connect an unknown resistor here. So connect an unknown resistor here, and I have to determine the unknown resistance value. Okay, so after connecting unknown resistance, just you can see two knobs here. You can see two knobs. Okay, you can press these two knobs at a time. Press this knob and this knob at a time. When you press this knob, both the knobs at a time, the galvanometer, it may deflect right side or it may deflect left side. Okay, it may deflect right side or left side. So simply what you do is, you can see here different multiplying factors are being provided here. Okay, different multiplying factors are being provided here. So you can see into 1000 ohms, into 100 ohms, into 1 ohm, and into 10 ohms. So you just simply since we don't know the resistance, first of all you just check if as soon as you okay, you just set some value. For example, you just some 100 ohms. For 100 ohms, just move this knob to 1. Okay, move this knob to 1. 1 into 100, you will get 100 ohms. Okay, so when you move this knob to 1, after moving that knob to 1, press both the buttons at a time with 2 fingers. Okay, so check whether the galvanometer is deflecting left side or right side. Okay, so if the galvanometer deflects right side, you further increase the resistance value. You just move this knob to 2 into 100, you will get 200. So for 200, you just check whether the galvanometer is further deflecting right side, okay, or it is, if the deflection is decreasing. So you can see this is a zero deflection scale. This is 0. So if the deflection is further increasing, don't increase this. Don't vary this knob. You go to some lower value. Okay, you go to some lower value around here. You can see 10 is there. So you just increase to from 0 to 1. So it is already 101 ohms you will get. So check whether deflection is towards the 0 or away from the 0. Okay, so deflection is towards the 0 or away from the 0. If the deflection is towards the 0, you continue varying the knobs. You continue increasing the resistance gradually. If it is moving towards the 0, if it starts moving away from the 0, you stop varying the knob and try to reduce the resistance value, okay, that you are increasing. Okay, so while practically when you are doing, you will get clear idea. So I'm just explaining theoretically. So what you have to do is, initially galvanometer knob will be at, pointer will be at 0. Simply you connect the resistor here and set the sensitivity value low, medium or high. It is not in this image. And set some multiplying factor. So it is better to set the multiplying factor to 1, so that after whatever readings that you get, you have to multiply with the multiplying factor. If you set it to the 1, then you need not worry about the multiplying factor. Even if you forget to multiply with 1, it doesn't matter. That's why set it to 1. Okay, you can set any value. It's best to set to one value, 1. And later you just vary any resistance that you want. Okay, your wish, any resistance that you want to set, you set it and check the galvanometer deflection. Okay, so if the galvanometer is showing some deflection, it's okay. Okay, you set, once you vary, you set some resistance by varying any of these knobs. Later you just vary another knob, or you vary the same knob, increase the resistance, and check whether the pointer is moving further away from the galvanometer or moving towards the galvanometer. So what you have to make sure is, once the galvanometer deflects, it's later on, as you gradually increase the resistance, the deflecting point should gradually move towards zero. It should not move away from zero. Okay, so by when you based on which knob you are varying, because of the variation of which knob, the galvanometer point moves towards zero, that you have to check. Okay, when you exactly set the resistance value, if suppose my resistance is some 56 ohms, for example. Okay, suppose my resistance is 56 ohms, just for example. Okay. If my resistance is 56 ohms, so suppose initially I vary this 100 ohms knob, I set 100. So definitely galvanometer pointer may move right side or left side depending on so whatever value that I have, depending on whichever knob that I have varied. Suppose my pointer moves right side, so for 100 ohms. Now when I press these two knobs, the pointer will move right side, just for example. And if when I further increase this resistance to 200 ohms, and if my deflection is gradually increasing towards right side, then what I should do is, I must bring it back to the initial position. Okay, I must bring it back to the initial zero position, and I must try to increase some other knob, maybe 1000, or let me check some lower value. Okay, 10 ohms is there, so I will set 10 into 1, and if the deflection is low, so I will better prefer this knob. Okay, I will better prefer this knob if the deflection is decreasing, if the galvanometer deflection is decreasing and if it is moving towards zero. And further, if I increase 20 and if the deflection is further reduced, I will go for 30, I will go for 40, and later I will go for 50. Okay, so as soon as 50 ohms is reached, of course, you can see it is 56 ohms. So 50 has reached, so there will be very low deflection from the 0 point. So if suppose I go for 60, what will happen is, if I go for 60, it is greater than 56. Therefore, in the pointer which was on the left side, now it will move towards, which was on the right side, now it will move towards left side. That means that the resistance value has increased beyond the required value. Then what I should do is, I must go for 1 ohm scale. Okay, this is my 1 ohm scale. I must go for this, and gradually I should start to increase I must vary this knob to 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm, and 6 ohm. As soon as I set, I will erase all links. Okay, as soon as I set the correct, accurate resistance value, yeah. So as soon as I set the 50 ohms, this is my 50 ohms, as soon as I set this 50 ohms in this, 50, and 6 ohms in this, 6 ohms in this. Okay, so the galvanometer reading will show 0. So when I press these two knobs at a time, the galvanometer reading will show 0. This is how practically we do this Wheatstone bridge experiment. Okay, so if possible, I will make a video of doing this experiment practically, and I will upload it in my channel. So this is the operation of Wheatstone bridge. Okay, and theoretically, if you want to determine the unknown resistance, this is the formula: R equal to P by Q into S. This R is the unknown resistance, P and Q are the known resistances, S is the variable resistance. So you can determine the unknown resistance here by this formula when the bridge is balanced, means when current flowing through the galvanometer is 0. Okay, so current flowing through this galvanometer, it should be 0. So when no current flows through the galvanometer, when potential difference between this B and Q is 0, when there is no potential difference, no current will flow through this galvanometer. Therefore, I1 will be equal to I3 and I2 will be equal to I4, and you can determine R value. So the R value is P by Q into S. Okay, draw the diagram quickly and I will conclude. So if you can draw these diagrams later on by going to my channel. If anyone have any doubt, you just mention in the chat box. Do you want me to repeat the concept? Wheatstone bridge concept. Okay then, I hope you have been following. I'll just conclude.